Right. So, hi. Thank you for coming. I know there are some other sessions in parallel, and I appreciate you coming. Maybe you could come in closer. You have more time for questions, so that's great. So, I want to talk about cross-platform development. And I'm a software architect. I do a lot of computer vision for multiple platforms, and I want to talk to you about some methodologies and architectures that I developed over time to enable me to target multiple platforms. Now, the first question that comes to mind is, what do I mean when I say cross-platform? Because there are many different interpretations of what this might mean, and there are many different target platforms that one might have to target with the same app or similar similar functionality. So if we go to the lowest level, we can think about custom hardware, custom chips like ASIC chips, and then when we start going higher, we get to embedded systems and mobile systems where we have multiple different operating systems, different chips, different types of processor architectures. Very often we get heterogeneous architecture, so we might have GPUs and CPUs both on the same chip or on the same board. Of course, on desktop, we have Windows, Linux, OS X, which are just the main desktop operating systems, but there are other types of operating systems. And these days, we can't ignore things like browsers, which have their own abilities to run computations, and they are a very important platform that we might want to target the same type of functionalities. So up until a few years ago, we had things called browser plugins. Maybe you remember ActiveX controls back in the days of Internet Explorer. Google tried something called the native client version. And of course, today, JavaScript and WebAssembly basically became the de facto standards. But we can go even higher in this hierarchy and think about cloud applications. So we're not running on some closed machine. We're running somewhere else on somebody else's computer. And there we have servers. We have Docker containers, Node.js, serverless type of cloud applications. And all of these might have to be targeted by the same type of apps and the same type of functionality, especially the kind of apps which require more compute and less of the data retrieval type of applications. But that's not all, because these days we're seeing more and more platforms that are able and need and require computation. So we can think about our cars. And I'm not even talking about things like autonomous vehicles, which have their own embedded systems, but even car entertainment systems, that can run apps and interact with the user. We have IoT devices, robots, and like I mentioned, heterogeneous systems with CPUs and GPUs. So it's a very wide ecosystem where we might want to target our applications. And that's what I mean when I talk about cross-platform, when I say what platforms are. And I've actually had to write multiple applications which targeted many subsets of these type of architectures. So, and my claim is that C and C++ are probably the only viable languages for true cross-platform development, because many of these environments might have their own sort of native languages which you might need to work with, like Objective-C or Swift or Java. But that generally doesn't generalize to other platforms. So the main issue that you see when you go and try to figure out, OK, how do I structure my application? How do I structure my system in such a way? Then you go to all these popular websites that give a lot of very good advice from some very smart people. But generally, the kind of code and examples you see there is it's a mixture. It's a big spaghetti ball of combination of SDKs and API and techniques and algorithms. And it's very difficult to separate the functional parts from the business logic, from the API, from the platform specific, from the cross-platform parts. So, and that makes the code, the resulting code, really very difficult to refactor, very difficult to maintain. It's generally totally non-portable. And of course, things like testability and fixing bugs become so much more difficult. And one other aspect that's not generally considered is the mixing of skills. So we might have an app developer that's like a superstar in writing iPhone apps or maybe some kind of web applications, but he or she are not necessarily capable of doing some complicated business logic, or they're not the right person to think about other aspects. So we want some kind of methodology that can allow us to separate these aspects in a clean and clear way. And on top of all these issues, we have things like module boundaries, where we're actually running multiple types of binaries on the same systems, and we have to see what happens along these boundaries, because things like exceptions don't percolate between, let's say, DLLs and host applications. So there's a whole lot of things we need to think about when we're structuring a system in this way. Now, the system I want to show you, I fondly called it the Salami Method, because it's based about slicing our system so thin that everything becomes very easy to understand. It's very easy to build. It's very easy to maintain, and also built by different people. So different people with different skills can maintain separate layers, but every layer is generally very, very thin and very clear and does only one thing, which makes it transparent, and it's very easy to maintain. So the benefits that we're getting, and I'm running through because we don't have a lot of time, is the first and foremost is the dry principle. Have you heard about the dry principle? Don't repeat yourself. So we're going to try and keep the most common stuff common to all our system. So that includes things like business logic and a lot of, because I've seen mobile applications where you had a team of iOS developers and a totally separate team of Android developers, and they were basically duplicating the complete app for these different platforms. And of course, if you fix a bug, you find a bug in one version, then somebody else needs to go and to check whether the bug actually exists in the second code base, and then to fix it separately instead of fixing it once and having it automatically deployed to the rest of the systems. And again, the transparency, which really comes from the single responsibility and testability. So whenever our systems has very clear roles and very clear targets, then everything is much easier to maintain and to test. And of course, the business logic is totally isolated and shared. So as I said, as a byproduct, it means that whenever there's a new system, let's say Windows mobile operating system become the hot thing of 2019, suddenly, then our system is almost ready. We just need to pull in the new UI stuff, and we can bootstrap very quickly and be target ready. Or on the other hand, we might be able to target. I had clients that had desktop applications, and they want to suddenly run it in the browser, at the client-side browser. And this type of architecture makes it almost trivial to do. So there's a lot of promise here, and I want to show you. And of course, I'll be happy to take questions. As I said, developer skills. So we can have different people working on different aspects, each one maximizing the strength and their skills. And it's good for the company. It's good for the developers. It's good for the system. And making everything very easily refactorable. Now, this is the gist of the talk, right? So if you take one thing away from this talk and you want to print out just this part, just this table, and it will help you remember what I'm trying to say. And it basically shows these layers that I'm talking about that I'll go over one by one during the talk. So at the bottom, we have the cross-platform core, which is really the business logic. And at the top, we have the host application. So that would be the UI part, the things that the user interacts with. And in between, we're going to talk about the different aspects that we have to consider. Now, the important thing to remember is that not every application is going to need every layer as a separate implementation layer. This is very similar to if you know the OSI networking layer concept. It's the same thing. Some applications might actually use thicker slices, but the aspects that I'm going to talk about do exist in every system. And a common question that I get sometimes is, yeah, but I'm using things like Swig, or I'm using some kind of automatic code generation system, or some kind of abstraction layer. So what I'm going to talk about is, if you're the one who's designed this abstraction layer, you're probably going to have to think about these things. If you're working with something like Swig or in Skipton, then maybe you can skip off some of these layers. For example, Objective-C can handle C++ code directly, so you don't need multiple layers. But that's one of the reasons we're thinking about this in layers, which build one on top of the other, and each one brings us closer to our target. Now, the first layer we want to talk about is the cross-platform C++ core. So this is where our business logic resides. This is where we apply the best C++ design idioms. We use our design patterns and the beautiful coding practices. We have a bunch of unit tests. And really the focus, as I say here, is in solid, maintainable, well-designed architecture. The things we're thinking about is how this is our company IP. This is the code that's going to go forward for years with within our company. And we want it well maintained. And of course, it should be totally cross-platform. But we know C and C++ basically compile to everything. So that's generally not the main idea. But we're not going to add platform-specific interactions here. So if we need some kind of more platform-related things, we abstract it in such a way that we don't tie it down into the cross-platform part. And generally, I use this is typically compiled into some kind of static library. So this is the thing that maybe most of us enjoy the most writing, and it's want to keep it elegant and simple, or at least maintainable. Now, the second layer, at the corner there, we can see those layers. And now we just skipped from the bottom layer up to the second layer, which I call the cross-platform public C++ interface. Now, this is kind of a shifty thing, because many systems don't actually need this as a separate layer. But I do believe this is a true concern that you need to think about when you're designing, when you're trying to target multiple platforms. And in this case, this is the public C++ API. Here we're starting to think of in services. We're starting to think in SDKs. We're starting to think about the users of our service. So it's less about the internal architecture of our code and more about how users are going to use our system from the API point of view. So in this case, we're applying good API design principles and focusing on the consumers. And here we're starting to think about how consumers are going to initialize and shut down some things like lifetime management sessions, how we're going to serialize and read things from files. So these are all issues that are generally more software, practically software related and not necessarily related to the beautiful architecture of whatever we're designing. It's also an opportunity to, for example, hide proprietary code, because this is something that we might give to a client as a compiled DLL or a compiled binary, which they might link against, although this is still cross-platform C++ code. But the client might be another team within the company. So we want to reduce, for example, some of the dependencies because the build system is unfortunately too complicated to deploy to everyone or things along these lines. Hopefully we're going to get modules. So this is a very classical place to think about modules, because this is the things we want to expose to the outside users. We don't need everything. It's just what's actually usable for the user. Again, the type of testing we do at this layer is mocking and unit testing the API itself. So we're not going to test that the functionality works, because we've already done that at the previous layer. But we want to make sure that building a session, for example, testing it, working it, making sure it starts properly and initializes, this is the right place to do it. The naming convention that I use, again, this is just a recommendation. Of course, you do whatever you like. Let's say I have some core CPP file, then I generally call it core API.cpp, which is a thin layer, typically on top of the basic C++ core. And as I said before, small projects, and the example I'll show you at the end, actually might skip this because the basic C++, the core, is sufficient to behave as this layer as well. But again, this is a concern that exists everywhere. So it's something that you might need to think about. Now, at this point, we get to the layer, we're going to have to stop. There is no more business logic.
from this point on when we're going up the layer stack. So at this point, there's because we're nearing the cross-platform boundary, it means that some systems might already interact directly with the public C++ API, which we just saw. So some target systems are not going to go further. So that means that we can't keep any business logic out of here. Because we don't want to duplicate and we don't want to have inconsistencies. So the third layer, which is still cross-platform in the sense that it's here it's the C API. So now we're moving from C++ to C, and we're trying to expose the more general or more powerful C++ APIs, which might be object-oriented or use some higher, a stronger type system, and such in a more C API, because really C is the basic library. There is no hardware that doesn't have a C compiler, right? Even if there's no C++, anything from the tiniest microprocessor for the washing machines generally has a C compiler. So if we need to go to the lowest level, or for example, interact with other languages, for example, we want to expose to Python or some Ruby or many other scripting languages, then generally working through DLLs with a C API is pretty much, in many cases, the only way to do it. So in this layer, we're going to take the public C++ API we saw before. We're going to wrap it, again, in very, very thin wrappers. And we're going to see some examples to give you so that I'm not just hand-waving here. And expose this C API, which is much easier to bring up to the cross-platform level. So in this case, would use extern C for linking ABIs. ABIs is the application binary interface. It's for C, it's standardized, and most compilers can interact and build them without. It doesn't matter which compiler you use, what compiler settings. The ABI is stable, and things like type conversions. Now we have to start thinking about lowering the type strength of our system to the basic primitive C types. So this is the place where we do the type conversions. And again, it's very, this is the place where we do it. So we don't need to think to have, to lower the type safety of all of our system. We just do it in some very isolated places. So we have much more control and less chances of messing about. So if we want to move from strings to character arrays, we know where it happens, and we can manage that. And I'll show you some examples in just a minute. As I said, object lifetime management, that's kind of the most difficult thing we need to think about when you're using C and there's no objects, there's no automatic shared pointers, and we have to think about allocations. Maybe we're using globals or singletons. We can use opaque handles. There are many ways to do it. And this is the place to think about them. Now, things like C++ can overload on the same function names, C can't, so we have to start changing function names. Again, with regards to testing, we can mock and unit test the C API. It's generally very simple because we're not doing actual functionality testing. It's just making sure the API performs the way we think we want it to. And the nice thing is that since in C and C++ we separate between headers and implementation, so the header files, the API itself, can be very C-like and very low level, but in the implementation we might immediately go to lift up the types using things like std span, or GSL span coming up in C++20, or moving directly to or string views as views to arrays. So immediately we're lifting, and let's see some examples just to make it a little bit more concrete. So we have a typical something that header file. It has 4 functions. They're inside the extern C because we want the C ABI. And I have 4 functions. The first 2 in the C, we'll see in the implementation in a minute, but we see they were both called init something because C can't overload on the same function. And this is what it would typically look like. Now, the way I think about the C in the air quotes is I like to think about it. It's not really C. It doesn't have to be like true C. It can be, you see, I kept the string here, although I might use a character star, and I'll show in a minute why I did it. It's just because I wanted to have different examples within the same snippet. So let's say we have process buffer, which takes a pointer and a size,
And the way we might implement this type of thing, again, it looks like a wall of code, but there's actually very little code here. This is just the implementation of the 4 functions. We include the relevant headers. And in this case, I just have one object. It's a global object. So think about it. It lives in the DLL memory space, and it's allocated once. I can initialize it, process some buffer, and ask it whether it's ready. So the implementations are generally just calling the member functions of this global object. Of course, if we need to handle multiple objects, we would need something like shared pointers or a proper opaque handle management. And in case we don't have default constructors, then we might use std optional or unique pointer if we want to allocate it on the heap. Again, this is the place to think about it. It's very difficult to get lost because all the functions are extremely thin. I'm not doing anything very complicated here. So we're just calling, you see there's one method called init here and another init here, but they have different arguments. So I'm actually, that's why I needed to change the names. Process buffer, like I mentioned, uses std span. So immediately, already in the implementation of this layer, I'm lifting my pointer plus size into a higher level abstraction, a stronger type, which means that everything underneath will be more type safe and more strongly typed. Right. Questions? Does that make sense? All right. So up to now, we moved up to the middle of our diagram, and everything up to here was cross-platform. So the blue part is cross-platform code, which generally compiles on all of our target platforms. Now we're going to move into the realm of non-cross-platform code and see how we're going to structure that in such a way that we can leverage and still get the manageability and maintainability, refactorability, testability that we were discussing in a more platform-specific way. Right. So the next layer is what I call the platform boundary interface layer. And as I said, this is where we're actually going to start touching platform-specific code. So this is where we might have different developers interacting with our code. Not necessarily, because often you need something that's someone who specializes in knowing how to do interop between the platform and the code. But still, you might separate. Somebody might do the web targeting, and somebody else might do the mobile app. And at this point, we're starting to think about conventions and constraints that come from the target platform. So we might have to convert between types because for example, JavaScript supports only doubles, right? And the C++ or C, we have integers, we have floats, we have multiple different types of numbers. And this is where we have to think about them. And we'll see some examples in a minute. Similarly, things like conventions, like function naming. If anybody's here done any NDK, Android targeting, then the functions need to be named in a certain way, and there are certain data types that you use to do this type of a J and I interaction. So this is where we do, and also it's a great place to set up logging logic. So there are many logging libraries that have very generic backends that you can cross-platform, and then only hook in platform-specific implementations at the beginning. So this is the great place to hook in your logging infrastructure for each particular platform and still get the same logging infrastructure underneath that works for all platforms. This is our module boundary, right? The wall, because this is where really the last place where we're going to see C and C++. So we have to think about interoperability with the external system. And things like exceptions can't escape. So we need to catch them and handle them and think, how are we going to percolate errors? How do we report errors? Do we report errors? Do we just crash? So these are all things that we need to think about. And regarding to testing, I don't know. I have an open question on Stack Overflow with no answers for the past probably 5 or 6 years. I don't know how to test this part. So if you have any ideas, come and talk to me. And yeah, so naming is pretty obvious and trivial. And let's see some examples. So we have the same, I'm going to use the same example I used before. We want to expose our foo session functions to, for Windows or Linux DLL, or shared object file. And in this case, most of the code here is code that comes from the platform. So we might have some kind of define called DLL Export, which is set to DLL import or export by, I actually have CMake generate this stuff for me. So, but it's typical, the way you do shared objects on Windows or on Linux. And again, we have to append this some kind of name so we don't have name collisions within the DLL system. And for example, on Windows, I chose the file name is lpcstr, which is a Win32 string type. I just wanted to show because here we already live inside the platform-specific code, so it's OK to use the more native or more, if we're doing iOS, it would be, I don't know, NS string or something like that, right? Objective-C. So that's the type. It's OK to use this one because we're already doing a platform-specific code. Now, let's say let's look at the implementation. So again, it looks like a little bit like a wall of code, but there's really just 4 lines here. If you look just at the returns, it's just calling the functions we saw before. And for example, we can see that this function just passes the LPC string file name into the init from file name, and Windows automatically converts that to a car string for an STD string. And the rest are simple calls. So there's no surprise here. No surprises here. Let's see another example. Oh, by the way, I'm using what's called the try block, a function try block. You see that the try and the catch are outside the main body of the file. I like using that style when we're writing DLLs, and I'll show an example in a minute why. But this is kind of an obscure feature that nobody knows. So this is the same code that's targeted to Android. And it looks like a lot of code, but 99% of it is mandatory by the JNI convention. So I don't have any extra code that I had to write. It's ugly, but the ugliness stays in this file. That's the main thing with the pasta code, that the ugliness is contained only in this file where I have to do the JNI interaction. And you need to have this macro at the beginning. We have to use J for JBoolean or JObject and all these types that come from the Java JNI system. For the names have to be appended with the Java underscore. So it's very similar to what we just saw when we were targeting Windows DLLs, but it uses the conventions and the constraints coming from the Android JVM. So for example, if you're passing we saw init from file name requires a string. But this string is actually going to come from Java. It comes from the JVM, the Java virtual machine. And the way we need to get the characters of a string requires some work involving the environment. The environment is like the hook into the JVM. So I'm using some kind of helper RAII utilities that I wrote to help me get this string and convert it to STD string. And then the function is going to be released properly from the JVM. Similarly, I have something called the JNI byte array adapter, which again is the RAII buffer tool to let me access and really keep the code as short as possible. It's very difficult to write something shorter than this when really each function it's just one line or 2 lines of code, right? So it's ugly, but the ugliness comes from the interaction and from the target system. It's not our code. This is it's as maintainable as can be. Another interesting thing here, you can see with the function try blocks, I'm actually returning something called exception handler, which is a special class that I wrote, which handles the exceptions for all of these things similarly. And in fact, what it does, it catches the C++ exception and creates a Java exception on the JVM and copies the information into that Java exception and then percolates the exception in Java. So whoever is going to be using that is going to be able to catch an exception within the JVM, not knowing that this was actually translated from a caught exception inside the C++ code. But of course, you can put any handler you want. You can just return false or whatever. Right. So our next layer is, this is like, we're not in Kansas anymore, okay? So we're not, this is, I know this is C++ conference, but now we're totally in alien territory. This is, we're already on the target platform, right? So this is the, in this case, we're running on the device itself. This can be a mobile phone. We have different hardware, different operating system, different language, different conventions, different styles, different idioms running the same code. And most of these target systems have what I call kind of ironically the native interface, because the word native is overloaded with two totally opposite interpretations. Because if you think about it, iOS, the native language for development on iOS would be a Swift or Objective-C. In Android, the native thing you develop is like for the developers who are working for that platform, it would be Java. But in fact, all of these languages, what they call native is really C code, which is touching the bare metal of the processor. So that's why it's kind of ironic that the word native really talks about both things simultaneously. And this is what we're going to use. It's the native interface. So it's how the local platform, the platform-specific SDK, allows us to load these DLLs or load this native code or C++ code into our binary. And that usually allows us to do some kind of reflection of the functionality. And it's usually very, very low level, because we saw most of these systems only interact at the C level. So the kind of testing we do here, of course, is integration testing. We can write kind of a test suite with our target platform, loading this DLL or loading this our code, and checking that it works. And of course, the file names here are already, you see, we can have Java or C# or JavaScript. So we're not even, there's no more C++ here. And let's see an example. This is a very, very trivial example. This is Java, but I think the C# is almost exactly the same. So we have some kind of public class foo session. We call the system load library with the name of the DLL. We load it, and then we define these public static native functions, which just expose the DLL functions. So if you've ever loaded a dynamic library function, this is what it looks like. The interesting part, as you can see, that we have the file name. Now, this is the capital S string, which is a Java type. This is the Java string. It's not a character array. Or when we want to pass an array of bytes, it's a byte array buffer. So this is already the Java world. And our JNI interface took care of making the conversions, and we converted from the JNI types to our C++ types wherever it was necessary. So this is really a direct mapping of the JNI interface in this example. Now, the last layer that we have to, that I generally like to write, is what I call the interface wrappers. Because as we saw, every platform has its own idioms. I mentioned this before. They have their own style, their own types that developers are comfortable working with. And very often, these low-level interfaces that come from the DLL are not, don't necessarily fit the mindset of the developer. They're too low-level, and you don't want your developers messing about with such low-level and this type of low-level types leaking into the main application code. So I generally like to add this interface wrapper layer, which allows us to let our users work within their normal, comfortable zone of types and things as they're used for each particular platform. So I'm going to show an example because it will make a lot more sense. So this example actually uses slightly different. These are not the same functions we saw before, but it's the same concept. Let's say we have a class that is a face detector for some video processing application. So it reads, there's some kind of video stream analysis, and we want to extract where there's a face. And the algorithm actually does the face detection and returns the position of the face. So at first, this is the Java code for Android, right? So we're going to load the DLL. It's called the native face detector. And we are going to expose this function called getFaceCenterPoint. Now remember, this is just the JNI version. And since it uses a C interface, the only thing it can really return is an array of floats, because it's very low level. It's only primitive C++ types. But working with a float array that has to be of size 2, and it represents the x and y coordinates of a face, is not very comfortable for somebody who's developing a UI and needs to draw a square there, for example. So it's too low level, and it ruins the abstraction. So the interface layer, the native interface layer that I'm talking about is really about adding this additional function. So you see, it's in the same file. It's not even a separate implementation file. Now I'm actually using the conventions of the platform. So maybe my function names would be with the uppercase get face center point, and the return type is in fact not an array of floats, but it's something called pointf, which comes from the Android graphics library. And our user, I could actually make this private or something like that, so the user doesn't even know that this function exists, and they only interact with this high-level function. Now you might think that why is he showing us this? Because it's so trivial and obvious, and maybe my APIs are sufficiently good that my users are smart enough and they can use the low-level APIs. But in fact, most of Android is implemented this way. I mean, Android isn't written in Java. Only the apps are written in Java. Android is a C++. It's a Linux system written in C and C++. And most of the hardware APIs are actually implemented in C and C++ and exposed via the Android SDK in exactly this way. So there are good examples, and you can see that even if you're used to working in Java with these high-level API functions, really underneath what they're doing is this type of conversion. So we're bringing the low-level C-type interfaces into the high-level Java class-type system. Okay, so I think that's the important thing to remember. It might appear almost very loose and trivial and thin, but this is how all of the Android ecosystem really works under the operating system. Right, so to summarize, I kind of flipped the layers on its side now. So on the left, we have the core C++. Of course, the last layer is the application layer, right? This is what we don't actually have to write ourselves. So this is the developers who are doing the UI, doing the UX, doing the rest of the application, and loading our files. But now we've done this kind of motion of going down in abstraction level and expressiveness and type safety, but we brought it back up. We lifted everything back up into the platform system in such a way that we still kept all of the business logic shared between everything, and wherever we need to do the conversions, we're smart enough to do it in the optimal way for each platform. So now I have a few more minutes, and I wanted to show you an example. So do you know this? Have you seen this parrot meme before? You've seen the party parrot? It's a very common animated GIF on the webs. And I decided that I'm going to try, and I found the original video where this came from. It's a real parrot, actually. And I said, OK, let's see if I can apply that type of color rotation on the actual video in real time. So I wrote a simple a function called rotate hue. I used OpenCV. That's it's a computer vision image processing library. And I'm not going to go into how the implementation, into showing the code of the implementation, but I have a function called rotate hue. It takes a 3-channel 8-bit image, returns another image with colors that had this color cycling rotated, and it has a third variable which sets the speed of the rotation. So the larger the value, the faster the numbers are going to, the faster the color change is going to happen. And some memory related function. So I wrote this function, and I have a simple main in C++ which I can run and load a video, and it works on my desktop machine. But my goal was to have it run in the browser. Because when you think about OpenCV, which is a giant C++ library, the browser doesn't seem like the typical target that you would think about. I'm talking about front-end JavaScript. doing real-time video processing in the browser, in your browser. But again, this when I'm thinking about the Salami method, it really allows me to do a lot of things that were generally quite difficult to do otherwise. So I have a lot of big walls of text. I'm not planning on actually discussing all of them. But I just want to show the layers. And this function, we can think about this is both my core C++ API. This is my, and the public API, and even the C API. So here I rolled everything. It's just a single function. So I'm not going to separate it into 3 different implementation files just because I said so in the slides, right? So, but we are thinking about all the aspects that I mentioned before. So the aspects are always there. They don't go away when you have to target multiple platforms. But in this case, it's just a single file. And when we're targeting the web, or in this case, I'm going to use Skipton. Have you heard about Skipton? Skipton is it's a fork or a clone of LLVM or in Clang, which targets the output is not binaries for CPU. It's actually a version of JavaScript or WebAssembly, which can run in the browser. So it's like a type of binaries that can run inside browsers. And it allows us to do a lot of the conversions from C++ code or any other code that's supported by LLVM into running inside most modern browsers. So this would be the boundary interface layer. We have some global objects for the images. This saves us from having to allocate and reallocate images every function call, because this is C code. We don't have objects that are alive. So in this case, I'm just saving them globally. The function interface here, it needs this. There's some macros related to Skipton, and you can see that the types that I'm passing are relatively low level. So we need the width and the height, and there's some kind of buffer types that are related to the pixels. The interesting thing is that, as I mentioned, JavaScript doesn't know numbers that are not doubles. But it also doesn't know pixels and images that are not in the format of RGBA. So every pixel in an image that you have in the DOM tree in your browser actually has 4 channels, including A is the alpha channel. It's kind of a transparency thing. But our function actually processes only 3 channel images in the BGR color space, which is like inverted colors. So we said that the boundary interface layer is where you actually do the type conversions between different systems. And this is exactly what I do. So I'm taking in these 4 channel buffers, and then I'm calling color conversion to swap the buffers, swap the channels, and remove the alpha channel. So, and then the only thing that actually does any work is calling our C function rotate hue with the number of steps, which also gets passed from outside. And then I just copy back the numbers into the values of the pixels back into the output frame, again, in the JavaScript in the format that JavaScript expects. So you can see that the only thing that happens here beyond calling the actual function is really the type conversions, which are platform specific. And this is the right layer to do it in. And OK, so now we have to go into JavaScript. I'm not a big JavaScript developer. This is based mostly on Stack Overflow copy-paste technique you might have heard of, the design pattern. The only interesting part is really calling module is the name of the object that comes from Skipton. It has a method called rotate colors, which is the way Skipton compiled the function we just saw previously. And it calls it with the width, the height, the offset, the actual pointers to the data, and the color change speed, which is a variable that comes from the external JavaScript. Most of the code here is only related to memory management. So I'm not going to go into it. I have a blog post about it if you're really interested. And all that's left really is the host application. And now what's the host application for the web? It's just an HTML file, right? It's a web page, a static web page. That's all it is. So we have some kind of a div that I think it just means, OK, put an element here. I'm going to load the JavaScript files. This is the compiled binary. This is the adapter that we just saw in the previous slide. We have some local script that makes basically passes the video name, and I'm adding a slider so we can change the speed in real time, right? So I'm not just going to rotate the colors. I'm actually going to have it interactive. So we're going to see it live, changing live. So this is like real time, true real time video processing. And this is the the slider, right? So the values get updated into update color, change speed, just changes the value, right? So, and that's all there is to it. Let's see it running. Right. Can you see it? No? Here we go. Right. So on the left, this is the original video. It's I actually didn't do anything. This is just a regular HTML video tag. So you put the video tag, you say this is the name of the file, this is what you get. The video starts playing automatically. On the right, these are frames that my JavaScript is actually calling the code, and you can see that the colors are rotating. So every frame that's shown here gets hooked into the real-time video processing, passed into the function. A new frame which has shifted colors is generated and displayed on the side. You can see there's a slight delay, especially because there's PowerPoint running in the background. And this is our slider, right? So if I go to the slider and I can move it to the right, you can see that the colors start changing faster, right? And I can go to the all the way to the left, and then it gets stuck. So you see, this is real-time video processing in the browser running C++ code, which it didn't take a lot of work to, well, at least the separation makes it relatively easy to understand what we're doing. And if we're stuck on some particular aspect, it's not hard to know where the problem is. And I think that's the main message I'm trying to say. And thank you. So if you have any questions, I'll be happy to. I mean, we're such a small group, so just feel free to ask. And I'm good on time. Yeah, sure.
Actually, two questions. What you do for the callbacks, especially because on the Android, every time it's not simple that you just call a function and just wait for a return. Many times you need a callback. Then for each function you go deep, you need another one go up.
Yes, it's true. I didn't want to go. That was kind of beyond the scope.
And also the streams. For example, if you want to send the video stream down, at the same time you get another stream up. In the simplest case in the GNI, it's very difficult to just make this stream working. And then if you add another layer, then you have to do this job 10 times, like, I don't know, do it twice, but at least one way go down, one way go up for the stream.
Okay, you had multiple questions.
Yeah.
The first one was about callbacks. Now, a callback mechanism really depends on the type of system you're working in. So if your system is multi-thread, truly multi-threaded, and you're expecting the callback to return on a different thread, you usually have, it means your system is multi-threaded, so you can use threads within C++ as well, and have it multi-threaded in that way. I've written an app which generates callbacks on different responses from callbacks on different threads. The way it does it is it actually opens an STD thread inside the C++ code, returns immediately to the caller. Whenever that thread is finished, it actually hooks into the Java JVM, creates a Java thread, and connects it to the current C++ thread and generates the callback there. That's possible. I've written JNI interfaces that mirror abstract interfaces. So I have like a callback function that derives from some abstract interface, and like a true virtual function, both on the Java side, percolates through the C interface, calls some virtual functions on the Android side, which also return the. So everything is possible, and this actually makes it much more easier to maintain, because the separation is so obvious, and you know what you have to do where, and it helps you manage what the things you need to think about. I'm not saying the code isn't horrible. What I'm saying is that your users don't see the horrible code, and you have a much easier life maintaining this type of code. So, and about the streams, I'm not sure I understood, but I think I'm not sure how you can do it. I mean, nothing I said here is something you don't have to do today anyway. The only thing I'm showing you is that it's possible to cut things thin enough so that it's more maintainable and it's more obvious what needs to be done where. So if you can do it in some other way, you can probably do it here as well. Because it's more about what aspects we need to think of when we're treating a system. And if you're doing concurrency, well, concurrency is hard always, you know, so yeah. I hope that answers the question.
What's the performance penalty? Because you add a lot of extra layers to your program, and I totally agree that it's more maintainable for different groups, but you have to have a performance penalty because you're not using the native code.
But you are using the native code.
Yeah, but you have to go through a lot of layers. So
yeah, but the layers are mostly conceptual. Most of the functions are inlined, and sometimes they're not even separate functions. It's the same function. As I said, I'm not actually doing anything you wouldn't be doing anyway.
Yeah.
I'm just showing you how to, change the structure of your code so it's more obvious what you're doing and it's easier to maintain. I'm not doing anything. I mean, maybe you might have one extra function call, but that's like, if you're already passing through a difficult JNI interface, then that's really, you're talking about microseconds, even in a mobile device. So there is no obvious penalty that I could see here. So I might be wrong, and I'll be happy if you see one, but yeah. Okay, yes?
Like the second question regarding that, I've never used EM Skipton that you use for connecting between the JavaScript and the code. Is it this EM Skipton just translates C to the Java? Because
no.
How you call a C function from the browser?
Okay, so Skipton started out as a project in Mozilla, and what they did, they took the LLVM backend for Clang, and they basically take the optimized AST, or the optimized intermediate, the IR, the intermediate representation for generating binaries. And instead of writing a binary for a particular processor, the first thing they did, they wrote something called ASM.js. It's a subset of JavaScript, which is highly optimizable by JavaScript, by the JavaScript engines like V8 from Google and other process. I think yeah. You know what? Let's move it a little bit over there. Let him get settled here. Sorry.